Hey guys, so I'm here today with Eddie the monkey. Hi guys. And we're going to be looking at the quantitative side of magnetic fields. Okay, we've got all the direction stuff, the right-hand rules, you got that in the main class, but Eddie and I are going to work through some of the numbers, all right? Now, you may be wondering why his name was Eddie. My daughters named him. I don't know why. There's absolutely no resemblance, is there? Don't answer that question. All right, you ready to go, Eddie?
Yeah, this is easy.
All right, here we go.
Hi, Eddie.
Eddie's done. All right, so here we go. This is the formula that we're going to be using over the next little bit, okay? This is the magnetic force, which is equal to the charge of the particle that's moving times the velocity of the particle that's moving times the sine of the angle times the strength of the magnetic field. All right, so again, charge of the particle, the moving particle, the velocity of moving particle, okay, the angle is the angle between the velocity and the magnetic field. All right, and we'll look at one of those in just a second here. Really, the important part, what you noticed as we went through all the directional stuff, is that everything had to be perpendicular, right? The force that we ended up getting ended up being perpendicular to the direction of the motion of the particle, right? It was perpendicular to the field, right? And so what we want is we want the perpendicular component. Just like all the other times in this class when we've used sine or cosine, it's not about the sine or the cosine, it's about getting the right component of the vector that we're using. And we want the component that is perpendicular to the vector, all right? The vector of the velocity. So this is the angle, the sine is just to make sure that it's perpendicular, and B, we haven't seen B yet, but B is the magnetic field. Strength. All right, so that's what we've got. We're going to go ahead and use this in a couple of examples, just to kind of give you an idea of how it works. Okay, so here's our first one. We've got a proton, which is cruising along with a speed of 2 times 10 to the 6 meters per second. And he's going to go through a magnetic field of 1 millitesla. So it looks small, but we'll get an idea of that later. 1 millitesla, which is, we see the dots. The dots are pointing this direction, so that magnetic field is coming out of the page. So let's talk about first the direction, and second, we'll talk about the magnitude. So we already know right-hand rule, proton is going this way. We've got the magnetic field, which needs to be coming, you see the tips of the arrows, so the arrows are coming towards you, so we need the magnetic field to be coming towards you. Notice that my finger is still pointing the direction of the velocity, fingers, magnetic field, and the force then is downwards. So we do know that the force is downwards. All right, and now we're going to throw the numbers in, right? This right here says that the magnetic force is equal to the charge of the moving particle. This is a proton. A proton has the same charge as an electron, except it's positive instead of negative. This is what we call the elementary charge. It's the smallest charge that we know is possible to exist by itself. And that would be 1.6 times 10 to the negative 19th coulombs. So that's Q, 1.6 times 10 to the negative 19 coulombs. We've got the velocity of the moving particle, which was given to us right there. 2 times 10 to the 6th meters per second. So I'm just going to leave it there. And sine of theta. So here we'll notice that the particle is going this way and the field is coming this way. So the angle between those two, that's a right angle. If we were to see this from above, you would see the particle going this way. You'd see the field going this way, which is a right angle right there. So this is a right angle. Sine of 90 is 1. And so that we're not going to need. And then we've got the strength of magnetic field, which is 1 millitesla. So we'll go 0.001 because we haven't seen the units yet of Tesla. That's because we didn't do any numbers for magnetic field yet. Just understand that T Tesla is the SI unit for the magnetic field strength. So now that we've got all those put together, you should just be able to type that into your calculator. Beep, 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 beep. And we get our final answer, which hopefully is 3.2 times 10 to the negative 16th. And it's a force, so it's in newtons. And you'll notice that's a pretty small force. The magnetic field, sometimes it's shown as Fm, other times it's shown as Fb, so that it matches the symbol for the B there, for the magnetic field strength. So it's up to you. Either one of those is acceptable. Though very often, because we also have like a buoyant force and things like that, very often they'll use the Fm to show force of the magnetic field. All right, so that's the first one. Pretty straightforward, right? Let's go ahead and look at another one. All right, so this time we've got an electron. Okay, so the charge is still going to be that 1.6 times 10 to the negative 19th. Okay, but this time it's negative. Notice that when we do this, we're not going to pay attention to any of the positives or negatives here. The reason why is because the positives and negatives really are just giving us a direction. It'll give us the direction of the force. It'll give us the direction of the velocity, right? And we are already going to take care of the directions with our right-hand rule. And so we can kind of ignore it. If you want, you can go ahead and throw in a bunch of absolute value signs here. Just throw in a bunch of absolute value signs. So we're just going to use the positive values there, okay? And so direction will come from our right-hand rule, all right? So we've got the electron moving down. Let's do the direction first because we know how to do that. So we've got the electron going down. We've got the magnetic field, which is going to be my fingers there. You can't bend your fingers backwards. That's cheating. Okay, so if I want the field to go that way, I'm going to have to turn my hand around this way so that my field can go, or my velocity can go down and my field can go in that direction. Okay, so the fingers always have to go in towards your palm. They're not allowed to go backwards. Okay, so we got that, and you'll notice that my thumb is now pointing towards the board. So into the page. So the force on that electron, notice I was using by the way, I was using my left hand rule this time because it was an electron. You could just as easily use your right hand and say, okay, going down, field is this way. So on a positive charge, it would be towards you. So therefore, a negative charge should be into the board. All right, so no problem there. We've got into the page. Let's go ahead and put the numbers in it now. Okay, so we know that the force is going to be equal to the charge, which is 1.6 times 10 to the negative 19th. And remember, we're going to go ahead and just leave it positive because the negative, all it would do is change the direction, and we've already decided the direction. Okay, we've got the velocity. The velocity is 5.3 times 10 to the 6th. And then we've got the sine of theta. Now this time there is an angle, right? The magnetic field and the electron are not perpendicular to each other. So it is this angle that's going to be important. And remember, what we want is the part of the magnetic field that is perpendicular to the velocity. It's all about perpendiculars here when we're talking about magnetic fields and forces. And so you'll notice that's going to be the opposite side, which is why we're using sine of theta there. And so we'll multiply it by sine of theta, which was 50. And then we'll multiply by the strength of the magnetic field, which was given to us as 3.2 millitesla, so 0.0032. And that should then allow us to get the magnetic force. And the magnetic force, you go beep, 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 and hopefully you get 2.08. I only did two sig figs there, so I'm going to go 2.1 times 10 to the negative 15th newtons. So there you go. So the basics of using the mathematics is pretty straightforward, right? Just making sure you got the right numbers, you got the charge of your particle, you you've got the velocity of the particle, you've got the angle between the velocity and the magnetic field right here. And last of all, that you make sure that you've got the strength of the magnetic field. Remember that B is the strength of the magnetic field. It's not the force of the magnetic field. That's actually what we're solving for when we solve for the FM here. All right, awesome. Let's have a look at one more thing. You may have noticed that in all of the examples we've done so far, and in addition to everything that we've done up to this point, we've kind of just ignored gravity, right? We haven't said, oh, well, what are the forces? Oh, I got an electric force and I've got a gravitational force. Or, oh, there's a magnetic force and a gravitational force. No, we've kind of ignored gravity. Now, not to give it a bad rap or anything. I mean, yeah, I mean, it's pretty straightforward what we've been doing so far. But let's have a look at what effect gravity has here so that we have a little bit better idea. So I've got one last question here that we're going to work through that's going to help us understand, hopefully a little bit better, this idea of gravity, all right, and why we've been ignoring it all along. So I've got an electron. It is flying through space at 2.2 times 10 to the 6 meters per second. So similar to the speeds that we've been looking at in the previous questions, right? It has given me the mass of the electron, 9.11 times 10 to the negative 31st kilograms. And the question is, find the direction and magnitude of the magnetic field. And my question is, find the direction and magnitude of the magnetic field that is going to balance gravity. Okay, we know that as an electron flies through the air, that gravity is going to act on it, right? Any objects, any masses are going to feel the effects of gravity. So let's go through and do a little bit of math here and see if we can figure out. First, we are going to look for the magnetic field, but in order to get the magnetic field is in this equation, but I'm going to need to know what the force of the magnetic field needs to be in order to balance gravity, right? As this electron is going forward, I've got gravity pulling down. And then what direction will the force, what direction does the force of the magnetic field need to be to balance gravity so that my electron can fly in a straight line? Hopefully you're saying, well, the force, Mr. Bywater, needs to be upwards, right? Gravity down, magnetic force up. That allows my electron to fly along in a straight line. Okay, so let's determine the direction. Let's determine the direction of the magnetic field first. So knowing that the force needs to be upwards. All right, right hand rule. I've got, sorry, I'm going to use my left hand because it's an electron. So left hand, velocity going this way. I want the force to be upwards. So that's my thumb, right? So I'm going to turn my hand so that my thumb points upwards. And what direction does the magnetic field need to be? Well, it could be any of these things here, right? You see my fingers kind of wiggling around, and my pointer and my thumb can still be in the right directions. But the easiest situation is to say, well, some of it, a component of it, has to be out of the page, right? So what direction? Out of the page. All right, you could have just easily used your right hand. You could have said, let's go this way, force upwards, therefore magnetic field into the page. But because I use my right hand for positives, it's the opposite of into the page, which is out of the page. All right, so you get comfortable with whether you want to switch back and forth, positives and negatives, or if you just want to use one hand for everything and make sure that you're paying attention to the right direction or switching the direction if needed. Okay, so we got the direction. The direction is out of the page. We're going to keep it straight out of the page just to make it a little bit simpler when we do our forces here. All right, so now we want to be able to calculate the magnitude of B. So the magnitude of B, remember we've got the magnetic force is equal to the charge times the velocity times sine of theta times B. Now, I do have at this point, it's an electron. So I know the electron is 1.6 times 10 to the negative 19th. So I do know my charge. I do know my velocity there. The sine of theta, we said we were going to make it perpendicular just to make it easiest. Sine of 90 is 1. So that guy is 1. We'll go ahead and take that out. But in order to find the magnetic field, I need to know the magnetic force first. Now, this is why we did our force diagram. Remember that? Those good old days when we were doing all those force diagrams? Yeah. So let's look at our force diagram here. Notice that the magnetic force needs to be equal to the gravitational force. So in order to know what the magnitude of my magnetic force is, I just need to go figure out what the magnitude of the gravitational force is. So we know that the gravitational force is equal to mg, mass times the acceleration of gravity. All right. So we know the mass of an electron. It was given to me right there. Ain't that convenient? You were wondering why it was there. You thought I was just tricking you. Here we go. 9.11 times 10 to the negative 31st. Oh, that is a big one. Times g, which is 9.8. Or 10. If we've been using 10 in class, that's fine as well. I'm going to use 9.8 because this is a little bit prep for AP, and that's what we use in AP is 9.8 meters per second squared. Go ahead, calculate that, and what we get is that we need the force of gravity to be 8.93 times 10 to the negative 30th. That's a pretty small force there, right? So that force of gravity is what we're going to put into this equation down here, because we want the force of gravity and the magnetic force to be equal. So we go 8.93 times 10 to the negative 30th is equal to Q, which was 1.6 times 10 to the negative 19th, times V. That velocity was given to us, the 2.2 times 10 to the 6th meters per second. Everything's in SI units. That's why I'm not writing down my units. I know that this force, because I used kilograms and meters per second squared, that's in newtons. Because that's in newtons, this is in coulombs. That 2.2 times 10 to the 6th is in meters per second. Everything's in SI. We got rid of the sign. So then we put our magnetic field there. And then you should be able to, sorry, that's a little bit long for a vector sign. You should then be able to calculate for B, divide by the 1.6 times 10 to the negative 19th. Make sure to divide by the whole thing at once. Don't go divided by 1.6 times 10 to the negative 19th, because your calculator will divide by the 1.6 and then it will multiply by 10 to the negative 19th. So be careful with your calculator there. Divide by those two numbers. You should then be able to get that the magnetic field is equal to 2.54 times 10 to the negative 17th Tesla. So the magnetic field required to balance gravity is 2.54 times 10 to the negative 17th Tesla. Now I want you to look at that. Isn't he cute? He's so tiny, so cute. Everything's tiny, so we're cute, right? So that's so tiny, so cute compared to these, right? Before we said, oh, that 1 millitesla, that's not a very big number. But look at how much magnetic field is required to oppose gravity. It's so tiny, so cute, right? So that's enough to oppose gravity. So if you have this much, gravity is nothing, right? This is times 10 to the negative third, so it's 14 times bigger than that. And so really, the field, the magnetic field, when we have magnetic fields and we're talking about, particles, this is different when you're talking about larger masses like trying to float a magnet or a train on a maglev, something like that. You're going to get into things that then require much larger magnetic fields. But when we're talking about particles, gravity is nothing, right? Gravity is so tiny. Gravity really is the weakest out of all the forces that we have. Okay. And sometimes you're like, yeah, but gravity it keeps me on the ground. Yeah, but you can jump, right? You can overcome the force of gravity during the time that you are pushing on the ground. Gravity is tiny. It's minuscule. It's nothing. It's true that it's always there. That's the problem. Well, problem, I say problem, that's a good thing. But that's really the idea there. Recognizing we were able to, this was a great question because, number one, it allowed us to work the other direction with our equation. We were solving for the field instead of the force. Okay. And secondly, it helped us understand why in all of these magnetic field questions and electric field questions, why are we ignoring gravity? Because really, in that amount of time, it doesn't matter. It doesn't matter. All right. Thanks. Hopefully that was kind of a neat thing. I hope you enjoyed it, and I'll see you next time.